So steps are already given, and using the steps we can draw the root locus diagram. We start with the problem number 1. So here is the problem statement. Draw the complete root locus diagram for the system whose open loop transfer function is given by gh of s is equal to k by s into s plus 5. So this is very simple problem. Start with a simple problem, slowly increase the complexity in the problems. So very simple problem, we need to draw the root locus diagram for this. Step number 1. Look at the given open loop transfer function in the pole 0 form or not. Yes, this is in the pole 0 form. Then you just write how many poles are there. P is equal to, in this case there are 2 poles, so P is equal to 2. Then what are the locations? S is equal to 0 and S is equal to minus 5. And there are no zeros, therefore Z is equal to 0. Take the S plane, and on the S plane then locate those poles. 2 poles are there, there are no zeros at all. Origin 1 pole and S is equal to minus 5, another pole. 2 poles are there. This is my step 1. In any problem, you have to locate poles and zeros in step 1. What is step 2? In step 2, we need to identify the area of root locus on real axis. Now, then area is it's very clear, from 0 to minus 5 we have area. So this is the area of the root locus. How to find the area of the root locus? So this entire real axis is divided into different segments. So that end is your plus infinity, right hand. Then after that origin is point, therefore plus infinity to origin is one segment, and origin is 0. 0 to minus 5 is another segment, minus 5 to minus infinity is another segment. So if you want to have the root locus in the first segment, that is from 0 to plus infinity, take any point in that, count poles and zeros, right to that. Then if you count poles and zeros right to that, there are no poles and zeros, it's even number for example. Therefore that particular area we don't have any root locus. Then between 0 and minus 5, take any point here, then if you take any point here, then count poles and zeros right off it. So if you count, there will be 1. So what we can say here, there is 1 means, so in this area we will have root locus. From again minus 1 to minus infinity, you will have even number, so no root locus area. So second rule says that only from 0 to minus 5 you will have root locus area. Step 3 is asymptotes information. You know P is equal to 2, Z is equal to 0, the number of asymptotes A is equal to P minus A, that is going to be 2. Now 2 asymptotes are there. Then we will find what is centroid. Centroid is the starting point of all asymptotes. Therefore centroid formula is sigma poles minus sigma zeros divided by P minus Z. So what will be that? We have 0 and minus 5, and there are no zeros at all, divided by P minus Z is 2, that is going to be minus 2.5. So centroid C is equal to minus 2.5. So on this S plane, you locate one point, say that point is centroid, you just C is equal to minus 2.5, put that in a rectangular box. So centroid we know. So once you know the centroid, then we can find out what are the angles. We know already when A is equal to, there are 2 asymptotic angles, and A is 2, those angles will be theta is minus 90 and theta 1, theta 2 is minus 270. What is this minus indicates? Minus indicates counterclockwise direction. So in S plane, the right side, that means from 0 to plus infinity, so this is the axis of 0 degrees. From there I can measure the angle in anti-clockwise direction, and that angle is your minus. So if you have plus, then you should take clockwise direction angle. Since we are taking all minus, therefore we take the minus value. So from here to here minus, and from here to here minus 90, minus 270. Therefore from centroid draw one straight line, that is A1, you say it is A1, that is nothing but your asymptote 1. Similarly 270 degrees is here, and this is A2, and we have A1 and A2 which are asymptotes and centroid. So this information is now available to us. So next is we are going to calculate break point. So break point is, So when you calculating, when you want to calculate breakpoint, look at the possibility of the breakpoint. What will be the possibility of breakpoint? Look at two poles. Here I have two poles in between root locus area. Yes, there is a possibility of breakpoint. We will calculate. So in the calculations we write 1 place gh is equal to 0. That place 1 place k by s into s plus phi is equal to 0. So you will be getting s square plus phi s plus k is equal to 0. Then we need to write is k is equal to f of s function. When you write k is equal to f of s function, we can write k is equal to minus s square plus phi s. Then if you differentiate it, dk by ds is equal to 0, it is going to be, so s square plus pi s becomes your 2s plus phi is equal to 0. So s square is 5 and you have s is equal to minus 2.5. So minus 2.5 is valid or invalid, let us check. So minus 2.5 will be in between 0 and minus 0.5. So minus 5. So 0 and minus will have minus 2.5. Therefore, there exists breakpoint. Whatever you are getting the minus 2.5, that is a valid breakpoint. For any point on the real axis, then you just locate that point on the root locus area, whether it exists in the root locus area, that will be the valid breakpoint. Now the breakpoint calculation is over. Then look at the next step. What is that? Imaginary crossover point. So if you look at asymptotes and also poles and zeros on S-plane, there are two poles which are there in the left of the S-plane and there are no zeros at all, and two asymptotes in the left of the S-plane only. Therefore, there is a possibility of having entire root locus in left of the S-plane only. So it cannot move to the right of the S-plane. We can say now there are no imaginary crossover points. Similarly, the next step is angle of departure or arrival. In this particular problem, there are no complex zeros and no complex poles. Simply we can write it as no angle of departure, no angle of arrival. Now, so we have all the information that is available to sketch the root locus. In the step 7, you are going to sketch it. Now, to sketch the root locus, look at whatever the things we have drawn on the S-plane. And I have s is equal 0 one pole, s is equal minus 5 another pole, and these two poles are the starting points of my root locus. And we know that there are two root locus branches which is starting at s is equal 0, which is going to start at s is equal to minus 5. Now, so centroid is available, asymptotes also available. So keep that in mind that you have asymptote like this. What do you mean by that asymptote? Yes, one of the root locus branch will go along with this, another root locus branch will go along the bottom asymptote. So that idea you should keep in mind. Now how to draw that? First of all, when k is equal 0, where are the two root locus branches? When k is 0, the first root locus branch I am taking at s is equal 0 to origin. K is equal 0, I have a root locus branch starting point here. As k is increasing, my closed loop pole has to move. So this s is equal 0 is the open loop pole. When k is 0, my open loop pole, closed loop poles are same. K is 0, open loop poles and closed loop poles are same. So my closed loop pole is here. As you increase k value, it has to move. What are the different possibles for the movement of this closed loop pole? One possibility is towards the right direction, another possibility is towards the left direction, another possibility is jump into the complex plane. For anything there are three possibilities only. Let us check all three possibilities. So this pole, it cannot move in the right direction because that is not root locus area, it is restricted. So if it is restricted, we cannot move right side, and it cannot jump into the complex plane because that point is not the break point. Only through the break point root locus branch can jump into complex plane. So it is not break point. The right side there is no root locus area and it has only one possibility. That possibility is moving left of that. Therefore, this particular closed loop pole, as k is increasing, moving towards the left direction. Yes, it is moving. Simultaneously at the same time, what about the other root locus branch? What this is doing? Oh, s is equal to minus 5, I have second root locus branch. Again there are three possibilities. It cannot move towards the left direction because here you don't have any root locus area. It cannot jump into the complex plane because this is not at a break point, and only one possibility, it can move toward the right direction. And this is moving towards the left, this is moving towards the right, both will come and meet here. This point is the break point. and at this break point they can jump into the complex plane. That is a break point. Is at the break point root locus branches can jump into the complex plane. So they jump into the complex plane. So after they entering into the complex plane, where they go? So you know the asymptotes now. So if at all, if zeros are available, yes, they try to look at zeros. If zeros are not there, what is the nearest asymptote to it? So nearest asymptote is this, which is going in upward direction. The another asymptote is going downward direction. So one of the root locus branch will take upward along with this asymptote. Another will go along with this asymptote. It is going along with this asymptote because your centroid and breakpoint both are same. Centroid is minus 2.5, breakpoint is also minus 2.5. Therefore, so they exactly follow. In fact, if you have asymptote over that, you have root locus branch which is going to plus infinity, and another root locus branch is going to minus infinity over the asymptote. Now, what will be this? Once you have this complete root locus sketch, what will be the conclusion? So, from this root locus diagram, if you look at the complete root locus diagram, the entire diagram is in the left half of the S-plane only. It is not moving to the right half of the S-plane. That means for all the values of k from 0 to infinity, all my closed loop pole, that means two closed loop poles are lying in left half of the S-plane. My closed loop system is absolutely stable system. It is very a strong system, we can say.